All right, and hello to you. Question. Dalton, Thompson, and Rutherford. These names may not have anything to do with you, or you've never heard of them, but I'm going to ask you a question. What do they have in common? Or at least as far as this video is concerned, what do these three names have in common? You're like, they all drive Jettas? I don't know. No, actually no, that's not it. They all contributed a diagram, if you will, or maybe a model that explains what an atom is. All right. I'm just drawing a quick representation here. Okay. So Dalton. This guy lived a long time ago. And he proposed that everything was made of atoms, and these atoms are like a little small ball, like a sphere that's hard, and you can't break it down anymore, and that's just what that represents. Again, we know that he was on the right lines, that yes, atoms make up everything. That's why you can't trust them. And so he wasn't entirely correct. Thomson here, he progressed on that idea that wait a second, there are different particles or different components to an atom. So it's not a little sphere, but you can break it down. And he proposed that the electrons were like the smallest particles, and this whole atom was like a dish of plum pudding, and these little raisins basically were suspended in the pudding. That's what that picture represents. Again, my art isn't the most reliable. Again, we know that, yes, atoms can be broken down into parts. We'll get to that in a second here. But as opposed to the electrons just being suspended somewhere near the atom or in the atom or the nucleus, not quite right. Rutherford, he was getting closer that the nucleus then had orbits. And we've seen this symbol. This is a very common symbol for nuclear or atomic things. The idea that then the electrons had orbits that they went through. And so, thank you, gentlemen, for contributing to what we know as far as what an atom is comprised of, and what we can understand from there. Now, first of all, this video is an overview, and yes, there's more to learn about protons, neutrons, and electrons, and even parts that go down further than that, quarks and all of those things. I'm not going to get into that, but in a general sense, I will be able to show you what an atom is comprised of, the three main parts, and their relationship to one another, and what that means for the atom as a whole. To do so, I am going to use the element helium. All right, if you think in a periodic table, you think of where that is. Helium would be in the upper. This guy right here, way up here. Not hydrogen. Hydrogen is atomic number 1. Helium is atomic number 2. And you're thinking, big deal, right? The atomic number in an element refers to how many protons are in that element. And so if there's an element that was found in nature and it had an atomic number of 2, we would know that it is helium. No questions. That doesn't change. The number of protons is the number, the atomic number. So when you think, boy, I found this element and the atomic number is 79, what is it? I can't just tell you that. Look it up on your own. But if something has 79 as its atomic number, then it's the 79th element, and it is whatever that is, because there's 79 protons. So helium has 2 protons. These are just styrofoam balls. I did not color them or anything. They just represent helium. Now, protons are positively charged. Yes, I'm sure about that. I am positive that they are positively charged. All right. Well, we know that all atoms have an overall charge of neutral. They aren't positive, they aren't negative. They are neutral. So, if you have 2 protons in a helium atom, and they are protons, as we know, are positive, well, then there needs to be 2 parts negative that would basically balance this out. You'd have the positive, then you'd have the negative, and then everything would be neutral. We would be good. Enter electrons. Okay? Size-wise, these aren't necessarily exactly what they would be, nor would they be this close. But the idea that there are 2 protons, so there will be 2 electrons. Now, again, that can change, and chemistry can get all out of whack that way. Don't worry about that. We're not going to get into that. But the number of protons is 2, so the number of electrons is also 2. But wait, there's a third part. Oh no, I need another hand. You take the atomic mass of an element, which we know helium to be 4.003. We're just going to say 4, just for rounding's sake. So we take the protons plus the number of neutrons equals 4.003. Well, again, we're rounding to 4. So 2 protons plus x equals 4. Simple math, 2 neutrons. So you're going to have 2 neutrons, 2 protons, 2 neutrons in the nucleus of a helium atom. And then you're going to have the 2 electrons that are going to be way out here doing their thing as far as doing what electrons do in orbiting. All of the space between the electrons and then the nucleus, this is the nucleus, not the electrons, but the protons and neutrons. All of that space between, that's exactly what it is. Space. There's nothing there. All right? Let's see if we can't show you in a... Here we go. It's a marble. It's a red marble. As you can see, it's about a ½ inch in diameter. Well, maybe 1 inch almost. If I were to take this, I live in Green Bay, and I live not far from Lambeau Field. So I take this and I go put this on the 50-yard line. Lambeau Field. There it is. All of the space, all of the rest of the field, all of the stands, the concourse, the scoreboard, the entire rest of the stadium is all empty space with the little electrons floating on the very edge, roughly speaking, of the stadium. So that's a comparison. Remember, in helium, you've got 2 protons, 2 neutrons. This is the nucleus of... So you take the nucleus, which is represented by this marble here. This then now goes at the 50-yard line of any stadium. If you live in a different stadium, or you live in some other country that soccer is your sport, put this right at the center of the field, right in the center. That's the nucleus of an atom. Then what you're going to have is you're going to have the little electrons whirling about at fantastic speeds. Just incredible. And I just found them. And these are going to be whirling around at just, again, incredible speeds. And so you're thinking, well, that's great. What does it have to do with us? Atoms make up everything. Everything that we are, everything that we can see, touch, feel, sense, is made up of atoms. Okay? The air that we breathe, the chair that I'm sitting in, the table that my computer is resting on right now, all of the books and games behind me, all of that, everything is comprised of atoms. And the fun part about chemistry is that we get to see how they interact. Why is it that sodium, which is the chemical symbol for sodium, is called Na, and then chlorine, which is Cl, why do they form a simple compound called salt? Why did they do that? Well, this isn't for that. To answer that question, that's not for this video. But the idea that it's the electrons. It's the configuration of the parts of the atom. And so it's really cool how all of that can work together. Helium is not super friendly in that helium is not super friendly as far as, it likes the way it's configured and it doesn't really feel like sharing and whatnot. Well, if you go down one element to hydrogen, so you've got a proton, you've got a neutron, you got one little electron. Hydrogen is a very friendly element. He likes to share this little electron, and so going around and whatnot, and but you get to learn about that when you're dealing with chemistry. But for this video, very simply, an atom will have X number of protons, X number of neutrons, X number of electrons. The electrons are the negative component, the protons are the positive component. Neutrons, as their name might suggest, are neutral. There is no positive or negative charge. And so when you have all of them put together, you have an atom, and that atom then is used, again, to in the creation of these different compounds and formulas. We can study how other elements will act with certain elements and what happens when they hit or mix. Do they hit? Do they mix? Or is it just nothing? And those kinds of things. And so it's fun. So I leave you with this. Two molecules were walking down the street. And one molecule, he trips on the curb and he falls over and he's like, oh man, I lost an electron. And his friend's like, well, are you sure? He goes, yeah, I'm positive. So, with that in mind, happy chemistry. And again, atoms, don't trust them because they just make up everything. Thank you very much. See you next time.